Hello everyone. So today we're going to discuss resistor circuits. Now you already know what a resistor is. It's a very common, very useful, simple circuit component. The circuit symbol is this, and a resistor can limit current. When there's current in a circuit, the resistance creates voltage across it. When there's a current through the resistor, it makes voltage across it. Also, the bigger the resistance, smaller the current. So one of the purposes of resistance in circuit is controlling current, right? So there are ways to increase current also by putting parallel resistance. You kind of know how this works, so we're gonna get into details today. So let's see what this slide's saying. A series connection has a single path from the battery. Series connection is one loop through each circuit element in turn, then back to the battery. So there's three resistors in the circuit. They can be just electrical resistors. There can be some other components like light bulbs or some other electrical equipment. So series means they are all back to back. The current goes to the first one, and then the second one, and then to the third one, back to the battery. So you can see the voltages. Each resistor has voltage across them, V1, V2, V3, and we know the voltage rule. In a single loop, it adds up to the supply voltage. So we'll go over a couple of slides and come to an equation. So the current through each resistor is the same, and that's true. In a single loop, no matter where you measure it, it's the same current. The voltage depends on the resistance. The sum of the voltage drops across the resistors equal to the battery voltage. Voltage drop, that's the other word we use, right? So let me go back to the previous slide. All right. So here you see, let me draw that. Here, 1, 2, 3, 1, V2, V3. That's current I. So the battery voltage, the supply voltage, can say V equals V1 plus V2 plus V3. Each of these voltages is the current through it multiplied by the resistance, right? The current times the resistance, and times the resistance 2 plus the current times the resistance 3. So that's what the next slide shows. So let's go back to that. And this is equals to the supply voltage. So this is another thing to remember. Same current, the voltages adds up, and if you multiply the current by each resistance, that gives you those individual voltages. Let's see what's next. So if we say that the total resistance of this entire thing, these three resistors, the total resistance, we can replace all that with a single resistor. We call it R total or R equivalent, and then connect that to the battery. The current in that circuit will be the same current, right? Whatever the current over here, if we put the equivalent resistance, the single resistance, it will have the same current in the circuit. So here I can replace this V with, instead of V, I can write the current times R equivalent instead of this. You see that this I cancels out, giving me R equivalent is the sum of the R1 oops, plus R2 plus R3. So if the resistors are in series, the total resistance is sum of the resistors. You just add them together. Remember the capacitor equation. This is kind of the opposite of that. If capacitors were parallel, you add all the capacitors. If resistors are series, you add all the resistors. Okay, pretty straightforward. You just add them all together. Okay, so let's move on. Now let's think about a parallel circuit. A parallel connection splits the current. The voltage across each resistor is the same. Alright, what does that mean? Now here comes the parallel circuit. Let me take a new page. Let's say we have three resistors parallel. R1, R2, R3, all parallel, and then goes to the back. Okay, so when resistors are parallel, they all will have the same voltage. If the battery is 5 volts, across each resistor there will be 5 volts. Current comes in and then it splits into 3 branches. Here we have 3 parallel paths, so there will be 3 paths of 3 lines of current. If the resistors are different, the current on each path will be different. So let's call it I1, I2, and I3. Now a couple of things to remember. Bigger the resistance, smaller the current. Right? So that means the biggest resistance will have the least current in them. The smallest resistors will have the highest current in them. If the resistors are equal, if R1 equal R2 equal R3, then all these I1, I2 and I3 will be equal. If 2 resistors are equal, they will have equal currents in them. If all 3 equal, the total current will be divided by 3, and like if you have like 12 amperes coming in, it will be 4 amperes, 4 amperes and 4 amperes. So the next diagram right over here on the PowerPoint, just replace the resistors with light bulbs. These resistors can be anything. So the current splits, right? I is different, V is same. These are the important things to remember. In the previous one, series connection, it's the same current but different voltages. How do you find the equivalent resistance, the total resistance for a series connection? So again, we can follow the same path. Here we know it's going to be the current that is adds up. So you write that total current is the sum of the 3 currents. And also we know that the voltage is going to be same. So we know that V equals IR, Ohm's law, and we can replace current V over R. So you replace each current I1 replaced by V over R1. Voltage is same as for each term. The total current is replaced by voltage over R equivalent. And you see that voltages cancels out. And then it gives you this final equation. So if the resistors are parallel, we want to find R equivalent, but we can find it directly. We start here, 1 over R eq, write it, R1, R2, R3, and then you solve this first, and then from this you flip the number, take the 1 over, take the reciprocal, you can find R eq. Okay, so for parallel, this is what we do. what we use. So again, all that information is good, but ultimately what you need is these two equations. So for parallel, the equation. For series, you just add all of them, plus R2 plus R3. And if there's more resistors, you keep adding them. Alright? Okay, what's next? It says an analogy. Here's a way to remember this. Well, I'll let you guys read it. Let's move on. Conceptual example, series or parallel. The light bulbs in the figure are identical. Which configuration produce more light? Which way do you think the headlights of a car are wired? Okay. Ignore the change of filament resistance R with current. Well, let's assume that the resistance does not change regardless of what current is going through it. So here we have two light bulbs. The diagram in the left connects to the battery in series. It's the same battery, a car battery, 12-volt battery. The other one, two light bulbs connected in parallel. Asking which configuration produces more light. So I want you guys to think about it and try to justify your answer, whatever the answer you come up with. Okay, let's clear this. In the first configuration, two bulbs are series. This is 12 volts. Bulbs are identical. This will have 6 volts. This will have 6 volts. In this configuration, this is 12 volts, this is 12 volts, because battery is 12 volts and they're parallel, so they both will have 12 volts. Which configuration produces more light? It's gonna be this one, because resistance is going to be same, right? For an example, if we say the light bulb has a resistance of let's say 2 ohms, right? So if this is 2 ohms, the voltage here is 6 volts, so the current is going to be 3 amps. This is also 2 ohms, so the same 3 amps. It's going to be the 2 amps in this circuit. Over here, 2 ohms and 2 ohms. What is the current? This one will have 12 over 2, 6 amps. This one will have 6 amps. Altogether, there will be 12 amps of currents. It's a lot of current from the battery, but if you look at the configurations, this is 6 volts, low voltage, low current. Here, high voltage, high current, more power, more light. This configuration will have more light in them. Which way do you think the headlights of a car are wired? That's also this configuration. Reason? In the first one, if let's say this light on the left goes bad, the light is bad, there's no current flow through the circuit, so this second one won't even work, right? So that's really bad. In the second configuration, even if one light goes bad, the second one still works, so you can still drive, like let's say in the night, you can still drive it to like a safe place and do something about it. But the first configuration is not good for a motor vehicle. Alright. Okay, let's move on. Here we have a problem with numbers. 100 watt 120 light bulb and a 60 watt 120 light bulb are connected in two different ways as shown. In each case, which bulb glows more brightly? Okay. Alright. Why don't you guys give it a try? It's pretty similar to the example we just discussed with the car battery and those light bulbs. So I'm not gonna solve this. I want you guys to work on that. Let's move on. Give it a try. Alright, so here's an example with numbers, series and parallel circuits. Okay, before we get to that, let's work on two very simple examples. So let's do that real quick. Let's say we have three resistors in series. 10 ohms, 20 ohms, 30 ohms connected to a battery of 12 volts. Question number 1, total resistance. Number 2, total current. Number 3, V on each resistor. Alright. Equivalent resistance Req, you just add them together. 10 plus 20 plus 30 equals 60 ohms. Total current, use V equals IR. 12 equals I total times total resistance, which is 60. So I equals 12 over 60. 1 over 5.2. I think so. 0.2 amps. Voltage on each resistor, V on each. First resistor, put V equals IR to the first one. V equals, the current is going to be 0.2, resistance is 10, so 2 volts. Second one, V1, V2, same current, 20 ohm resistor, so what, 4 volts, right? V3, same current, 30 ohms resistor, 6 volts. When you add them together, you see it comes back to 12 volts. Okay, let's try a series example. Parallel. Let's take same 3 resistors. And you know the rule, you're gonna work this first and then pause the video, work it first, and then look at the video. 30 connected to 12 volts. So the questions, let's see. R total, I total. Now this time there's no point asking voltage across each resistor because it's going to be 12. So I through each. Alright, so equivalent current, equivalent resistance, Req. You're going to start with 1 over Req, which is 1 over 10 plus 1 over 20 plus 1 over 30. I'm going to use the common denominator, which is 60. 6 plus 3 plus 2, 11 over 60. So Req, you flip it, 60 divided by 11, 55, 54, something like this ohms. Double check. So another thing to remember, when resistors are parallel, the total resistance is less than the smallest resistor. Here the smallest is 10. We have a total of 5.45, which is smaller than the smallest. The resistors are series. The total resistance is bigger than the biggest resistor. In the previous example, the biggest was 30. Our total was 60. Okay, so these are some little things to remember. Alright, total current. Now the idea is, this is like having a single resistor replacing all three connected to the same battery. So 12 volts and 5.45 ohms. What's the current? It will be the same current in this circuit. So the total current is this over here. Then it will be divided into three branches. And then they all come out and then will come back as the total. So what we need is this total current. So that's the same current over here in this simplified diagram. So V equals IR, 12 equals I total times 5.45, I total 12 over 5.45. So 2 point something divided by 5.45, 2.2 amps. Number 3, current through each resistor. We can use Ohm's law for each single branch. Starting from the first one, V equals IR. Voltage is going to be 12, current, resistance 10, so current is 12 over 10, 1.2 amps. Go to the second one. Again V equals IR, 12 equals I2 times 20, I2 is 12 over 20, so 0.6 amps. I2. Third one, I3 is 12 over 30, so that will be 0.4 amps. Now when you add all these together, it comes back to 2.2. Also you see, the smallest resistor has the highest current, 1.2 amps. The next one has the next big current. The biggest one has the smallest current. Okay? Alright, having said all that, here we have an example with things mixed up. Now you guys have worked with capacitors, so you know what to do here. Only thing is, don't mix up the equations, right? The total resistance, if they're series, it's kind of the opposite looking equation for the capacitor. Okay? Alright, so let me clear this. And let's work on this example. You should do it first. How much current is drawn from the battery shown? Okay, so resistor and then two resistors over here. $400 ohms, 500 ohms, 700 ohms, 12 volts. The total current I is here, I total, and then so that total goes through this 400 ohm resistor, and then it gets into two branches like this. Let's label them as I1 and I2. Alright, so find the total current. I total. For that, let's find the total resistance, right? So we start with our first step. Step 1, Req. So by looking at the diagram, you see that this 500 and 700 are parallel with each other. That should be my starting point, right? So I'm going to start here with 500 and 700 resistors. So I'm going to start writing this 1 over 500 plus 1 over 700. So what's the common denominator for these two? Looks like 3500, right? 3500 7 plus 5, so 12 over 3500. So Req is 3500 divided by 12, 3 point something, or 2.9 something, 290. Let's see, 3500 divided by 12, 291.6. Keep 2 decimal places at least. This is the equivalent resistance of this piece. So then it looks like 2 resistors in series, 400 here, 291.66 over here, and the battery. These two are in series, so you just add them together, comes down to a single resistor of 491.66 ohms connected to 12 volts. So V equals IR, 12 equals I times 491.66. Current equals 12 divided by that. So 12. Oh, what am I doing here? This is 691. Sorry about that. This is what happens when you do things in a rush. I'm trying to make it before 30 minutes. 12 divided by 691.66. I have 0.0173 amps, or I can say 1, 2, 3, 17.3 milliamps. That's the total current in this set. So the other things I can ask here is, what is the voltage across V across each resistor? I through each resistor. Current through each resistor, voltage across each resistor. How do I do that? Voltage across each resistor. Now for the first one, for the 400 ohm one, voltage across, we have the current through it. It's this same current, this total current goes through this resistor, right? It's the same current. So if you just put V equals IR over here, for that resistor we can find the voltage. V equals IR, so 0.173 times 400. So the voltage will be multiplied by 400, 6.93, 6.94. This will be 6.94 volts. Now these two are parallel, so the rest of the voltage, 12 minus 6.94, 5.06, it's going to be across both these resistors, right? The total voltage is 12. The sum of the voltages should add up to the total. The first one says 6.94, so the rest should appear over here, rest of the voltage, and the two resistors are parallel, so they both should have the same amount. Now it's asking current through each resistor. So for the first one, the 400 ohms one, you know the current, it is this 17.3 milliamps, and then it get divided into two branches. We know the voltage across each resistor. So for an example, 500 volts one, we know the voltage, 500 ohms one. So 500 ohms resistor, we know the voltage 5.06 volts. So using V equals IR, you can find I1. Doing the same thing, you can find I2. Or if you subtract I total minus I1 gives you I2. That's another way of finding it. Okay, we are at the 30 minutes mark. Let's see what else we have. This looks like the answer to the previous question. So the current in the circuit found to be 70 milliamps. So that's what we have. It's asking what is the current through the 500 ohm resistor. So give it a try. Let's see what else. Conceptual example, bulb brightness in a circuit. Let me make it a little smaller. The circuit shown has three identical light bulbs, each of resistance R. When switch S is closed, okay, so there is a switch here. I don't know whether you can see it. Yes, it's a switch here. How will the brightness of the bulbs A and B compare with that of bulb C? What happens when switch S is open? Use a minimum of mathematics in your answer. Okay, this is something for you to try. We can discuss this in class as well. What happens when you close the switch means the switch is connected, so there's current in the circuit. When the switch is open, what happens? What's the difference? So draw the diagram with open switch, closed switch, and do a comparison. Think about what happens, the total resistance, the current in the circuit when it is open and closed, all that. We can discuss this if you need to. Let's see next. Okay, so here's another good one. I'm not going to work on all of these. I will let you guys work on this, but try this one as well. Going to the next one. Okay, this you don't have to. We will discuss this in the next video. The internal resistance of batteries and how that comes into equation. So this, going back, this is the end for this video lecture. Series and parallel resistors combinations. We will work more problems in class. Alright, thank you everyone.